not only our own galaxy, but some of the most captivating galaxies in the entire universe. From silent dwarfs and colossal spirals to shattered remnants still glowing from collisions so ancient they feel like myth. We'll drift past halos of dark matter you can't see, past black holes that flicker like cosmic candles, and toward newborn galaxies shining at the farthest edge of what we can know. Some facts may leave you pleasantly unsettled. Others may settle into you as softly as the quiet after a memory. But all of them are real. Each sound a gentle echo from the vast, continuing story of the universe. And if this journey helps you relax, consider liking the video and subscribing to the channel. It helps other tired minds find these calm discoveries too. Now, if you're ready, let your thoughts float outward. Let your breath slow, like starlight falling onto a distant world, and let's begin. A quasar is a galaxy whose central black hole outshines all of its stars. In the hearts of some galaxies, black holes grow hungry. As they pull in gas and dust, that material spirals inward, compressing, heating, and glowing intensely. When the feeding becomes extreme, the galaxy ignites as a quasar, a blazing active nucleus so bright it can overwhelm the light of the entire galaxy around it. Some quasars are visible from billions of light years away, their light crossing unimaginable time to reach us. That power doesn't come from inside the black hole itself, but from the violence of matter on the edge of falling in. Around the hole, gas in the accretion disk can reach millions of degrees. Magnetic fields twist, tighten like invisible ropes. And sometimes, twin jets of particles are launched outward at near light speed, carving through intergalactic space. For a while, the galaxy becomes one of the brightest objects in the universe, powered by darkness, yet shining brighter than 1 trillion suns. Right now, the Milky Way is slowly consuming the Sagittarius dwarf galaxy. It's a quiet feast, measured not in minutes, but in millions of years. Sagittarius is a faint, spheroidal companion that has passed through our galaxy again and again, and each time it loses more of itself. Its stars are being pulled into long, delicate streams that now wrap around the Milky Way like ribbons, the fading signature of a galaxy in the process of being devoured. Sagittarius hasn't vanished yet, but it's thinning, stretching, and unraveling under forces it cannot resist. And those remnants matter. They help astronomers understand how the Milky Way was built, not in a single moment, but through the slow, steady accretion of smaller galaxies over cosmic time. The night sky we see is the outcome of countless such encounters, layered one over another across billions of years. Even now, our galaxy is still becoming itself, reshaped by what it pulls in and by what it leaves behind. Some galaxies don't hold just one supermassive black hole, but two. When galaxies merge, their central black holes may not unite right away. Instead, they form a binary system, two enormous masses orbiting each other in a slow spiral that can take millions of years to resolve. These pairs are difficult to detect, but astronomers have found hints. Two active cores shining as separate points, strange motions among the nearby stars, or subtle irregularities in the galaxy's light. Eventually, gravitational waves can drain their orbital energy, drawing them inward until they merge, releasing ripples through space-time itself. Until then, they remain hidden deep in merging galaxies, like twin hearts beating in the same chest, rare, powerful, and full of unanswered questions. And then there are galaxies that seem to have no stars at all, only dark matter. In the deep stillness between luminous islands of light, some galaxies reveal themselves without shining. No starlight, no star clusters, not even the faint glow of warm gas. And yet they persist, held together not by what we can see, but by what we can't. These dark galaxies are inferred through gravity, by the way they bend the light of more distant objects behind them, or by the subtle tugs they exert on neighboring galaxies and nearby clouds of gas. No one is entirely sure how they form. They may be galaxies that failed to ignite, or remnants of systems stripped long ago, but they drift like quiet ghosts, invisible islands of mass, present without illumination. Even the Milky Way is not immune to the pull of other giants. Though galaxies can seem eternal and fixed, ours is being gently stretched by tidal forces, especially from Andromeda, our nearest large neighbor, already drifting toward us through the dark. These tides act like the moon's pull on Earth's oceans, but on a far grander scale. Over millions of years, they can warp the outer disk of our galaxy, sculpt subtle ripples through its spiral arms, and nudge stars and gas into slightly altered paths. It isn't violent, it's slow rearrangement, the quiet reminder that nothing in the universe, no matter how vast, evolves alone. And when you step back far enough, the Milky Way is not even among the largest. Some galaxies are more than 100 times wider than our own. The Milky Way spans roughly 100,000 light years and holds hundreds of billions of stars, enormous by everyday standards. But true cosmic giants exist. Galaxies like IC1101 stretch for millions of light years, massive elliptical behemoths often found at the centers of galaxy clusters. They didn't become huge only by forming stars, but by swallowing dozens, sometimes hundreds, of smaller galaxies over billions of years. Their cores are ancient and dense, filled with old reddish stars, while their outskirts fade into darkness where solitary stars orbit in vast, slow arcs. These titans are rare and strangely quiet, but they remind us that our galaxy, for all its grandeur, is only average in size. Some galaxies also create new stars at rates that make the Milky Way seem almost still. Our galaxy forms about 1 or 2 new stars per year. But in starburst galaxies, hundreds, even thousands of stars can be born annually. These short, intense episodes are often triggered by collisions or close encounters when two galaxies pass through each other and compress their gas into dense, collapsing clouds. The result is a brief fireworks display. Ultraviolet light, glowing gas, heated dust, and a brilliant core packed with newborn stars. But starbursts burn fuel quickly. Many of these galaxies grow quiet again once their gas is consumed, shining fiercely for a moment before fading into calmer light. At the center of Andromeda sits a supermassive black hole, at least twice the mass of the one in the Milky Way. Most large galaxies have a black hole at their core, a region so dense that not even light can escape. In our galaxy, that central black hole is Sagittarius A star, weighing about 4 million suns. Andromeda's is larger, perhaps far larger. For now, both are relatively quiet, but in the past, they may have flared into brilliance. And in the distant future, when the Milky Way and Andromeda merge, these two black holes could spiral together and unite into a single, even more massive object, two galaxies, two hearts, becoming one dark center. Looking deep into space is also looking back in time. Light from the farthest galaxies we can observe has traveled for more than 13 billion years to reach us. In telescope images, those galaxies appear as tiny, faint smudges, dim, redshifted, and ancient. We don't see them as they are now, but as they were when the universe was young, only a few 100 million years old, small, chaotic, dust-filled, and blazing with early generations of stars. These newborn galaxies helped end the cosmic dark ages and seeded the structures we see today. Somehow, across all that time, their light still arrives, a message from the universe's early chapters, finally reaching our eyes. The Milky Way itself is surrounded by faint stellar streams, invisible rivers of stars left behind by galaxies it consumed. Our galaxy did not form all at once. It grew through mergers, and each merger left a quiet trace. Thin, elongated ribbons of stars wrapped around the galactic halo. Mapping these streams allows astronomers to reconstruct our galaxy's history, like reading scars from ancient collisions. The sky above us is filled with silent motion shaped by events billions of years old. And even now, we drift inside their echoes. In about 4 billion years, the Milky Way and Andromeda will collide and merge, not as a sudden crash, but as a slow gravitational dance lasting hundreds of millions of years. Andromeda is approaching at nearly 100 kilometers per second. Eventually, the two galaxies will pass through one another. Most stars will avoid direct collisions because space between stars is vast. But the galaxies' shapes will be distorted, their spiral arms tangled, and their gas clouds will collide, triggering waves of star formation. Over time, the system will settle into a larger elliptical galaxy, sometimes nicknamed Milkomeda. Our solar system will likely survive, though it may end up in a different region of the new galaxy. It's a quiet drama on a galactic timescale, and it has already begun. Some galaxies seem to be made mostly of gas. Not every galaxy is filled with stars. Some are ghostly systems dominated by cold hydrogen gas with very few stars to light them up. They can drift like dark clouds, detectable mainly through faint radio signals emitted by hydrogen. These dark galaxies may be systems that never quite began forming stars, or they may be leftovers from past mergers and collisions, reservoirs of invisible potential waiting for something to ignite them. And sometimes we only discover a galaxy because it bends light. When a massive galaxy lies between us and a more distant object, its gravity can curve and distort the background light, producing arcs, rings, and mirrored images. This is gravitational lensing, one of astronomy's most powerful tools. In the process, we can detect the lensing galaxy itself, even if it's too dim, too dusty, or too distant to notice directly. Some lenses reveal enormous amounts of dark matter. Others are simply placed in the perfect position at the perfect time. Either way, they become natural telescopes, magnifying the universe behind them and telling us about both the foreground galaxy and the distant light it reshapes. Galaxies can also launch jets of matter that stretch for millions of light years. When supermassive black holes feed, the magnetic fields can channel energy into twin beams of particles fired outward at near light speed. On radio images, these jets look like giant luminous threads stitched across intergalactic space. They can heat surrounding gas, reshape galaxy clusters, and influence star formation over immense distances. Some of the largest structures in the universe, born from a region smaller than the solar system. The oldest galaxies we've detected formed only a few 100 million years after the Big Bang. The early universe was dark at first, and it took time for gas to cool, condense, and ignite the first stars. Many early galaxies were small and chaotic, but some survived and grew. The earliest known candidates appear astonishingly soon after the universe began, their light traveling more than 13 billion years to reach us. They remain faint and redshifted, but with each new telescope, we push farther back into the cosmic timeline. The galaxies we find at the edge of visibility carry the story of everything that came after. Some galaxies are built from stars stolen from others. During close encounters and mergers, galaxies can strip stars from each other, stretching them into long tidal tails or sweeping them into extended halos. Over time, these captured stars can accumulate into new systems called tidal dwarf galaxies assembled from debris rather than formed from pristine gas. They may contain little dark matter and may not survive for very long on cosmic timescales, but for a while they shine with borrowed light, a patchwork made from the history of other galaxies. And yes, we've even found galaxies that seem to rotate the wrong way. Most galaxies rotate in the direction set by their formation, but some show counter-rotation. The disk turns one way, while gas or stars inside turn the opposite way. This often happens after a merger, when newly acquired material arrives with its own angular momentum. Instead of synchronizing, the motions remain distinct, a frozen twist in the galaxy's dynamics, evidence that something unexpected happened long ago. A single giant galaxy can host thousands of globular clusters, dense, spherical swarms of ancient stars. The Milky Way has about 150, but massive elliptical galaxies can have thousands, surrounding them like a halo of fossilized history. Each cluster preserves chemical signatures and ages from early cosmic eras, and by studying them, astronomers can reconstruct how a galaxy formed and what it absorbed. Some galaxies are powered by black holes that blink like beacons. Active galactic nuclei can brighten, dim, and flare on time scales of years, days, or even hours as the flow of matter into the black hole changes. In rare cases, we even watch galaxies switch on and off, transforming between quiet and active states, like a lighthouse flickering across the ocean of space. Even the Milky Way's spiral arms may be temporary patterns rather than permanent structures. In density wave theory, spiral arms are regions where stars and gas briefly bunch up as they orbit, like cars slowing in a moving traffic jam. The spiral pattern persists, but the material inside it changes. Other ideas suggest arms can form, break, and reform over time, shaped by star formation or gravitational interactions in past encounters. Either way, spiral arms are not static sculptures. They are living patterns, shifting, breathing structures in a sea of stars. And finally, dwarf galaxies can orbit larger galaxies like moons, orbit planets. And the Milky Way is no exception. It is surrounded by a population of dwarf companions, each containing anywhere from a few million to a few billion stars. These dwarf galaxies are gravitationally bound to us, moving in slow, patient orbits that last billions of years. Some of them, like the large and small Magellanic Clouds, are visible to the naked eye from the southern hemisphere, appearing as faint, detached patches of light against the dark. Others are so dim and diffuse that they have only been discovered in recent decades. revealed through painstaking sky surveys and subtle stellar motions. Some may be the shredded remnants of once larger galaxies, torn apart by tidal forces during close encounters. Others could be primordial fragments, survivors from the earliest stages of galaxy formation, small systems that never grew much larger. However they began, dwarf galaxies play a crucial role in the evolution of larger ones. Over time, they can be drawn inward, stripped of their stars and gas, and gradually absorbed into their host. But until that final merging occurs, they circle quietly through the galactic halo, tracing long arcs through invisible gravitational currents. Like moons orbiting planets, they are small companions, ancient travelers moving within a far greater story. Some galaxies are so faint they are nearly impossible to detect at all. While most galaxies would vanish without telescopes, a few remain ghost-like even under deep observation. These are ultra-diffuse galaxies, enormous in size, sometimes comparable to the Milky Way, yet containing only a tiny fraction of its stars. Their starlight is spread so thinly that their surface brightness barely rises above the cosmic background. In deep surveys, they appear as pale smudges, fragile and almost unreal. Only in the last few decades have astronomers begun identifying them in significant numbers using highly sensitive instruments and refined detection techniques. Their origins remain debated. Some may be failed galaxies that lost their gas early, never forming many stars. Others may have been stretched and weakened by gravitational interactions. Whatever their past, they drift through space almost silently, vast yet barely visible. And it is entirely possible that countless more remain hidden in the darkness, their light fading like a breath on cold air. In the crowded interiors of galaxy clusters, gravity can produce stranger outcomes still. Galaxies tug at one another, sometimes close enough to exchange stars, gas, or angular momentum. And occasionally, these interactions go further. A galaxy can be flung entirely out of its cluster, ejected at tremendous speeds into intergalactic space. These are runaway or rogue galaxies. Some are accelerated through complex gravitational encounters involving multiple galaxies or even supermassive black holes. Others are launched outward after repeated close passes that gradually build momentum. Once expelled, they become solitary wanderers, traveling through immense expanses of space with no nearby companions for millions of light years. Some trail elongated streams of gas and stars behind them, signatures of the violent events that cast them out. Others escape carrying only their dense cores, becoming isolated islands of matter adrift in darkness. They are difficult to detect, but a few have been identified. Each one tells a story of chaotic gravitational encounters in a universe governed by elegant but unforgiving laws. Even the calm center of our own galaxy may once have been far brighter. Today, the Milky Way's core is relatively quiet. Sagittarius A star, the supermassive black hole at its center, is subdued compared to the blazing nuclei of active galaxies. But evidence suggests it was not always so. In the distant past, it may have entered a more active phase, consuming large amounts of gas and radiating intensely, perhaps approaching quasar-like luminosity. Traces of that activity remain. Enormous gamma-ray structures known as the Fermi bubbles extend above and below the galactic plane, likely produced by energetic outbursts millions of years ago. X-ray echoes reflected off nearby molecular clouds hint at powerful flares in the past. Long before humans existed, the heart of our galaxy may have burned with extraordinary brilliance, briefly transforming the Milky Way into one of the brightest systems in its region of space. On the largest scales, galaxies follow a hidden blueprint, the cosmic web. They are not scattered randomly, but arranged along vast filaments composed of dark matter, gas, and galaxies stretching hundreds of millions of light years. Between these filaments lie immense voids, nearly empty regions where little matter resides. Galaxies form and migrate along these gravitational highways, clustering at intersections where filaments meet. This structure originated from tiny fluctuations in the early universe, amplified by gravity over billions of years. We have mapped parts of it through extensive galaxy surveys and computer simulations. But much of the framework, especially the dark matter that scaffolds it, remains invisible. Galaxies grow and evolve where these filaments intersect. The universe is not merely vast, it is interconnected. Not even galactic centers are always fixed. While supermassive black holes typically reside at the cores of galaxies, some have been found displaced tens of thousands of light years from their expected positions. And these offsets may occur after black hole mergers. When two supermassive black holes collide, they emit gravitational waves. If that emission is asymmetric, the newly formed black hole can receive a recoil, effectively being kicked from the center like a cosmic cannonball. In other cases, a binary pair may orbit slightly off-center within a disturbed galaxy. These wandering black holes are difficult to identify. Astronomers detect them through unusual stellar motions, displaced emission lines, or distortions in surrounding gas. They remind us that even the most massive anchors of galaxies are not always permanently fixed. Light from distant galaxies is stretched by the expansion of the universe. As space itself expands, the wavelengths of traveling light elongate, shifting toward the red end of the spectrum. For the most distant galaxies, visible light is stretched into infrared by the time it reaches us. This phenomenon, known as redshift, is one of cosmology's primary tools for measuring distance. The farther a galaxy lies, the more its light has been stretched. Some of the earliest galaxies ever observed are detectable only in infrared wavelengths. Telescopes, such as the James Webb Space Telescope, are designed specifically to capture this ancient redshifted light. Even after more than 13 billion years of travel, these galaxies still shine, altered by cosmic expansion, but not erased. Galactic cannibalism continues today. Large galaxies grow by absorbing smaller neighbors, stripping their stars and gas through tidal forces before ultimately merging with them. Deep sky surveys reveal faint stellar streams trailing behind galaxies, evidence of ongoing or recent mergers. The Milky Way itself is currently accreting dwarf companions. This process is not unusual. It is a fundamental part of galactic evolution. Galaxies are long-lived systems, but they are never static. They reshape themselves through interaction, sometimes growing by consuming what drifts too close. Some galaxies are hidden behind thick veils of dust. In these systems, dense clouds absorb visible light, obscuring internal structures. Many are sites of intense star formation, where new stars both create and recycle dust. In optical wavelengths, they may appear faint or even invisible, but observed in infrared, they glow brightly. Dust absorbs shorter wavelengths, and re-emits energy as heat, allowing astronomers to peer through the obscuration. Some of the most active star-forming galaxies in the early universe were discovered this way. Without infrared astronomy, we might never have known they existed. And within galaxy clusters, another force shapes evolution, the intracluster medium. Clusters are filled not with emptiness, but with a thin, hot plasma. As galaxies move through this medium at high speeds, they experience ram pressure, a wind-like force that can strip gas from their disks. Long tails of hydrogen can stream behind them, stretching tens of thousands of light years. Once stripped of gas, a galaxy loses its ability to form new stars and gradually becomes passive. Even in the seeming vacuum of space, galaxies can feel resistance. They are shaped not only by collisions and mergers, all but by the invisible environments through which they travel. And when that ancient quasar light finally reaches us, stretched by expansion, reddened by time, it doesn't just tell us that the early universe was bright. It also hints at something else the universe is full of: motion. Galaxies are not still paintings hung in space. They are rotating systems, vast wheels of stars, gas, and dust, turning around a common center, held together by gravity and balanced by orbital speed. Every star is in free fall, constantly falling around the galaxy rather than into it. But in some galaxies, that motion becomes almost unsettling. Out near the edges, far from the dense, luminous center, stars can orbit at speeds so high that if the galaxy were made only of the matter we can see, they shouldn't be there at all. They should drift outward and escape, each like sparks spun off a fast-moving grindstone. The visible mass, stars, glowing gas, dust, simply isn't enough to provide the gravitational grip required to keep those outer stars bound. And yet, the stars remain. They keep circling, calmly, year after year, million after million, as if an invisible hand is holding the rim of the galaxy in place. This is one of the quietest and most powerful clues in modern astronomy: the missing gravity. When astronomers mapped rotation curves, measuring how orbital speed changes with distance from a galaxy's center, they expected the speeds to drop off in the outskirts, the way planets slow down the farther they are from the sun. But many galaxies refused to behave that way. Their outer regions were moving too fast, too steadily, too confidently. The simplest explanation was not that gravity breaks, but that mass is hidden. A galaxy is wrapped in a halo of something we cannot see: dark matter. It emits no light, reflects no light, and, so far, does not reveal itself through any direct glow. But it does have mass. It does exert gravity. And it extends far beyond the visible disk, forming an enormous invisible scaffold around the galaxy, deepening the gravitational well and keeping those vast outer stars from flying away. In a way, the galaxy becomes a kind of cosmic illusion. The shining part is only the visible skin. The true bulk, the part doing much of the binding, is silent. And here, the story loops back to everything we've just traveled through. Quasars show us how gravity can turn infall into light, how a black hole's appetite can make a galaxy blaze across billions of years. Dark matter shows us the opposite kind of power: gravity without light, structure without glow, mass that does its work in darkness. One phenomenon dazzles the universe into visibility. The other holds it together from behind the curtain. So when you hear that some galaxies rotate so quickly their outskirts almost seem unanchored, it isn't just a strange detail. It's a doorway. It's one of the moments when the universe quietly admits that what we see is not what is there. only what is bright enough to announce itself. And in that silence, in that steady rotation that shouldn't be possible, we can almost feel the hidden architecture of the cosmos, an invisible halo, an unseen weight, keeping the galaxy intact as it turns and turns and turns into the dark. But that invisible mass holds everything together, even when a galaxy's outer stars are racing along at hundreds of kilometers per second. It's a quiet equilibrium, motion and mass in a kind of perfect balance. The faster the stars move, the stronger the unseen grip must be to keep them from drifting away. The galaxy turns, the halo holds, and in that silent partnership, speed on one side, gravity on the other, the universe reveals one of its simplest truths. Stability is often built from things we cannot see, and sometimes even the shape of that stability is strange. Some galaxies are polar ring galaxies, systems where one disk exists inside another, but the two rotate at nearly right angles. Most galaxies spin in a single, simple plane, like a record turning on a single axis. But polar ring galaxies seem to wear a second structure, a ring of stars and gas orbiting over the galaxy's poles, almost perpendicular to the main disk. These rare architectures likely form through interactions. When a galaxy passes through another, or when it steals gas from a neighbor, and that material settles into an entirely different orbit. Over time, gravity flattens that captured matter into a coherent ring, a luminous band that circles like a halo around a halo. Studying polar rings helps astronomers understand not only how galaxies merge and exchange material, but also how dark matter halos are shaped, because two rotating components angled against each other act like a delicate probe of the invisible mass surrounding them. From far away, they look like cosmic wheels turning on two axes at once, elegant, balanced, and unmistakably uncommon. Other galaxies take on shapes even more surreal. Some resemble enormous donuts, ring galaxies, where most of the stars form a bright circular band around a dimmer or nearly empty center. These rings are often born in collisions, when a smaller galaxy plunges straight through a larger one. The gravitational disturbance can send a ripple outward, like a wave spreading through a pond. That wave compresses gas as it travels, triggering new star formation in a moving circle. The result is a luminous rim, a glowing ring of newborn stars, and a central region that feels strangely hollow by comparison. Some rings are almost perfectly symmetric, others are warped or off-center, showing the violence that sculpted them. They're rare, but once you see one, you never confuse it with anything else. A fossil of impact, the still shining long after the moment of collision has passed. And yet, even with their odd geometry, these galaxies can remain stable. Stars still orbit in equilibrium. The ring still turns. The light traces the aftermath of an event that may have happened 1 billion years ago. But the system continues, gravity smoothing chaos into a new, workable arrangement. Elliptical galaxies tell a different story of motion. Unlike spirals, ellipticals do not have obvious arms or a thin disk. They are smooth, rounded swells of starlight, older, quieter, and often gas-poor. Inside them, stars don't move together in one grand, orderly rotation. Instead, their orbits are more random. Some loop in wide circles, others in stretched ellipses, crossing and weaving without a single shared direction. This organized disorder is often the signature of formation through mergers. When galaxies collide, the elegant rotation of disks can be broken, stirred, scrambled, and redistributed. Over time, the combined system settles into a more spheroidal shape, but without one dominant spin. From the outside, an elliptical can look like a calm fog of light. On the inside, it's a storm of countless independent paths, each star following its own private trajectory, all of them held together by gravity alone. And then there are galaxies that look as if they've been torn apart, mid-sentence. Irregular galaxies are messy, stretched, asymmetric, patches and knots of starlight without the clean geometry of spirals or ellipticals. Many are shaped by past collisions or close encounters, pulled and distorted by larger neighbors until any tidy structure is lost. Others may simply never have grown into a clear central form, forming instead as scattered clumps of gas and starburst. They are often rich in hydrogen and filled with young hot stars, active, turbulent, and alive with ongoing formation. From a distance, they can resemble fragments of something larger, but they are real galaxies in their own right. Small, restless systems still in the process of becoming. Sometimes that becoming happens in a blaze. Starburst galaxies burn through their fuel in a bright, brief cosmic flare. In most galaxies, star formation is slow, spread across billions of years. But in starbursts, it accelerates dramatically, hundreds, even thousands of times faster than normal, a merger, a close pass. Out of a shock wave, anything that compresses gas into dense clouds can ignite the burst. When it begins, stars form rapidly, flooding the galaxy with ultraviolet light and heating dust until it glows in infrared. The galaxy becomes brilliant, but the phase doesn't last. In a few million years, an instant on cosmic scales, the gas can be consumed or expelled, and the system settles again. What remains is a wave of new stars, a lingering warmth of dust, and the memory of a short-lived storm. Violent, beautiful, and gone almost as soon as it arrives. And when gas is lost, galaxies can fall into silence. A galaxy needs gas to keep making stars. When that gas is depleted, stripped away, or heated so it can no longer collapse, star formation slows and eventually stops. Some galaxies fade naturally over time as they use up their supply, but others are quieted by their environment, falling into clusters where gas can be peeled away or living under the influence of powerful feedback from black holes and massive stars. As the young blue stars die off, only older, redder stars remain. The galaxy still glows, but more softly, no longer creating new light, only drifting on the afterglow of its past. These systems are sometimes called red and dead, though they are not truly dead. They are elders, luminous fossils of earlier activity, preserved in calm. Yet even in a galaxy's brightest eras, creation is not gentle. When many stars form at once, they drive winds, streams of particles and energy that push outward. Supernovae intensify this, heating gas and blasting it away. In extreme cases, galactic winds can carry matter beyond the galaxy itself, into the space between galaxies. Now this removes the raw fuel needed for future star formation, altering the galaxy's destiny. Such winds are especially strong in starbursts and in galaxies with active black holes. We observe them as outflowing clouds of hot gas, streaming from galactic centers like a galaxy exhaling. One strong outflow can influence the birth of millions of future stars. One breath can change everything, and black holes, when active, can enforce silence on an even larger scale. As a supermassive black hole feeds, it doesn't merely shine, it pushes back. The energy it releases can heat surrounding gas or drive it outward entirely. This process, AGN feedback, can regulate or even shut down star formation by preventing gas from cooling and collapsing. In that way, a single object, tiny compared to the size of its host galaxy, can influence the fate of the entire system. Some of the largest galaxies may have stopped forming stars billions of years ago, partly because of this feedback. The center can look quiet, yet its past violence can echo through the galaxy's future. Even when a galaxy hides from visible light, it still leaves a trail. Many galaxies are surrounded by hydrogen, the most abundant element in the universe. Neutral hydrogen emits a faint radio signal known as the 21 centimeter line. By searching for that frequency, astronomers can detect galaxies that are too dusty, too faint, or too diffuse to stand out in optical telescopes. These radio signals reveal mass, rotation, and motion. They also help trace dark matter, because hydrogen, like stars, responds to the gravitational pull of invisible mass. Entire sky surveys can be built from radio observations alone, mapping hydrogen across space and time. In this way, galaxies can be seen by listening, invisible in ordinary light, yet quietly present in radio frequencies. Even the faintest systems leave a signature. Even in silence, there is something to hear. Some galaxies, in fact, are brightest in radio. They may host enormous jets driven by supermassive black holes, structures that can extend far beyond the visible edges of the galaxy, sometimes for millions of light years. Others glow in radio because of supernova remnants or cold hydrogen clouds. The radio sky can look entirely different from the optical one. Strange doubles, arcs, lobes, structures that the eye alone would never suspect. By observing in radio, astronomers uncover hidden architecture and energetic processes, and watch how galaxies interact with their environments in ways that visible light cannot reveal. Other galaxies are best found in the far infrared. Dust can block visible light, hiding intense activity behind thick veils. Yet that same dust will glow warmly in infrared when heated by newborn stars. Infrared luminous galaxies can be among the most active star-forming systems in the universe, but nearly invisible until infrared observatories open that window. Observing them in infrared lets us peer through dust and witness what is happening inside. Star formation, black hole feed, the dynamics of mergers. Some galaxies are concealed by the very material they create. They shine, but at wavelengths beyond our natural sight, visible only to those who know where to look. And when we look far enough, the universe changes its face. Our galaxies in the early universe, the ones whose light has traveled for more than 10 billion years, often appear smaller, rougher, and more chaotic than the graceful spirals and smooth ellipticals nearby. Many are still assembling, clumps of gas and stars in the act of merging, colliding, and igniting. Their stars are younger, hotter, and lower in heavy elements. Their shapes have not yet settled into stable forms. They are imperfect, messy, energetic, galaxies still finding their balance. And yet, these early systems laid the groundwork for everything that followed. Over billions of years, they grew through mergers, continued star formation, and gradual stabilization into the structures we recognize today. To see them is to glimpse the universe's youth. There was a time after the Big Bang when the universe was completely dark. No stars, no galaxies, only cooling gas. Then, slowly, first lights ignited, the first stars formed, the first galaxies began to gather. This era is often called cosmic dawn, beginning roughly a few 100 million years after the Big Bang. With powerful instruments like the James Webb Space Telescope, we are now beginning to catch sight of that threshold. Faint, distant galaxies from the universe's earliest light arriving to us after an unimaginable journey. And when you put it all together, rotation curves and dark halos, polar rings and collision-made circles, starbursts and silences, radio whispers and infrared veils, one message repeats gently again and again. The universe is not only what shines, it is also what holds. These early galaxies were small, chaotic, and astonishingly bright for their size, like sparks in a vast room that had only just begun to breathe. They formed stars at a furious pace, burning through their gas quickly, and in doing so, they started to ionize the hydrogen around them, helping to end the universe's long dark age, when neutral gas absorbed light and space felt dim, muffled, unfinished. Every image we capture from that era is more than a distant photograph. It is a brief, fragile glimpse of beginnings, the universe's first attempts at structure, its first experiments with life. The story is unimaginably ancient, and yet it is the foundation of everything we recognize. And the first galaxies likely did not rise by accident. They may have been cradled inside halos of dark matter. In the early universe, matter wasn't spread perfectly evenly. Tiny fluctuations in density seeded in the primordial cosmos and amplified by gravity began to grow. Where those fluctuations were strongest, dark matter gathered first, clumping into halos, invisible reservoirs of mass that carved out gravitational wells deep enough to pull in ordinary matter. Gas drifted into these wells, cooled, condensed, and, at last, ignited into the first stars, then the first galaxies. Without dark matter, those earliest galaxies might never have formed. The halos provided scaffolding, structure, stability, a gravitational shelter in a young universe that was still turbulent and expanding. And we still see the same pattern today, from the faintest dwarfs to the grandest spirals. Nearly every galaxy appears to sit inside a dark matter halo, an unseen skeleton shaping how galaxies grow, move, and endure. The first galaxies weren't simply lucky. They were held gently but firmly by invisible hands. Because without that invisible mass, galaxies would fly apart. Galaxies rotate. Their stars orbit fast. But when astronomers calculated how much visible matter, stars, gas, dust, was needed to keep those speeds bound, the numbers refused to agree. Outer stars were moving too quickly. By the usual rules of gravity, they should have drifted away into intergalactic space. And yet they didn't. That contradiction is where dark matter stepped out of the shadows. An unseen form of mass spread throughout and around galaxies, providing the extra gravitational pull needed to keep everything coherent. We can't see it directly. It doesn't glow, reflect, or absorb light the way ordinary matter does. But its effect is unmistakable. Without it, the edges of galaxies would unravel. Spiral shapes would not survive. Whole systems would dissolve or collapse into something else. Dark matter holds galaxies together, not just as an idea, but as the physical fact of their continued existence. Quiet, mysterious, necessary. Galaxies shine because of their stars, but they remain whole because of something we still don't fully understand. And once you accept that invisible framework beneath the visible beauty, the Milky Way starts to look less like a single object and more like layered history. Our galaxy has multiple components: a central bulge, a rotating disk, and a vast, diffuse halo surrounding everything. That halo contains some of the oldest stars in the Milky Way, many older than 10 billion years, moving along long, arcing orbits that carry them far above and below the disk. The halo has very little gas, so it forms few new stars today. Its population is quiet, faint, ancient. Many halo stars are metal poor, formed before the universe was enriched by repeated supernovae. The disk, by contrast, is younger, brighter, more metal-rich, with more orderly motion and ongoing star formation. By studying halo stars, astronomers can look deep into the Milky Way's childhood, back before the spiral arms were fully established, when our galaxy was still assembling. And some halo stars may not be ours in the original sense. Over billions of years, the Milky Way has collided with and absorbed smaller galaxies. Many of their stars were captured, folded into our outskirts, and set adrift on unusual paths. Those ancient mergers leave faint stellar streams and clumps, star trails with distinctive motions and chemical fingerprints. Astronomers read them like forensic evidence, a group moving together on a strange orbit, an element pattern that doesn't match local stars, a signature that whispers, "I was born somewhere else." These are survivors of galaxies that no longer exist as coherent systems, lost worlds whose lights were not extinguished, only relocated. The Milky Way is not a single structure. It is a memory made of many smaller histories, layered and intertwined, and we can map those memories. When the Milky Way absorbs a smaller galaxy, it doesn't happen all at once. Tidal forces stretch the incoming stars into long, curved streams, ribbons that wrap around the galaxy and can persist for billions of years, slowly fading into the halo. By measuring where these streams are, how they move, and what their stars are made of, astronomers can reconstruct the merger, where the dwarf came from, how it was torn apart, and roughly when the encounter happened. Some streams are broad and obvious. Others are thin and delicate, almost like pencil marks across the sky. Together, they reveal that the Milky Way grew not in one dramatic moment, but through repeated patient capture. This is part of why galaxies are natural time machines. Light takes time to travel. Look at a nearby galaxy, and you see it as it was millions of years ago. Look billions of light years away, and you see the universe as it was when it was young. The farther you look, the deeper into the past you fall, not by traveling through time, but by collecting ancient light that has been en route for eons. Every telescope is a time portal. Every faint smudge in a deep field image is a story sent from an earlier universe. And time becomes almost surreal when you remember how slowly galaxies tick. The Milky Way takes on the order of a couple 100 million years to rotate once. The sun orbits the galactic center at roughly 220 kilometers per second, completing a full circuit in about 225 million years. A galactic year. Since Earth formed, we've gone around only about 20 times. In a single galactic orbit, entire ages of life can rise and vanish. Dinosaurs appeared and disappeared within roughly one galactic year. Continents drifted. Species evolved. Civilizations, if they could be seen from afar, would flicker like brief reflections on water. The sky feels still only because our motion is shared by everything nearby. In reality, we are always moving, carried along inside a vast, slow wheel of stars. But that wheel doesn't spin like a solid disk. Galaxies are loose, dynamic systems of stars, gas, and dark matter responding to gravity. And what astronomers found was startling. Beyond a certain radius, outer stars often orbit at nearly the same speed as stars closer in. The rotation curve stays flat instead of dropping. This was one of the strongest clues that enormous mass exists beyond what we can see. Mass spread through a halo extending far past the luminous disk. That halo, dark matter again, acts like a hidden foundation stabilizing the whole structure. Without it, fast-moving outer stars would not remain bound. The galaxy would fray at the edges. This is how dark matter revealed itself so clearly, not by shining, but by governing motion. In the 1970s, astronomer Vera Rubin studied spiral galaxy rotation and found the same stubborn pattern again and again. Outer stars move too fast for visible matter alone to hold them. Something unseen had to be there, vast, distributed through and beyond the galaxy. Even today, much of what we know about dark matter comes from its gravitational influence, shaping rotation curves, binding clusters, bending light through gravitational lensing. We still can't see it directly, but we can read it in what galaxies do, in their speeds, their stability, their refusal to come apart. And so the story ties back to the beginning. The first galaxies formed inside dark matter halos, and modern galaxies still live inside them. Galaxies shine with stars, but they stay whole because of an invisible architecture underneath. A universe that looks like light is, at its deepest level, a universe held together by what does not glow. That invisible mass keeps them together even when they spin at hundreds of kilometers per second. It's a quiet balance, motion held in place by gravity you can't see. The faster the outer stars race, the stronger the unseen pull must be, tightening its grip without ever shining back. In that tension, speed versus weight, the galaxy finds its shape, and the cosmos leaves a signature, not in brightness, but in what refuses to fly apart. And sometimes, galaxies don't even agree on a single axis. A rare few become polar ring galaxies, systems with two disks at nearly right angles, like one galaxy wearing another as a tilted halo. The main body rotates in its familiar plane, while a second ring of gas and stars circles over the poles as if it belongs to a different world. These structures likely form through encounters. A passing galaxy donates material, or a near collision tears out gas that later settles into an orbit the original disk never had. Over time, gravity sculpts that captured debris into a clean, rotating band, two independent streams of motion layered in deep space, elegant and unnervingly stable. Astronomers love them because the ring becomes a tracer, hinting at the three-dimensional shape of the dark matter halo that must cradle both systems at once. Other galaxies wear their violence more plainly. Some look like cosmic donuts, ring galaxies with hollowed centers and bright circular rims, often formed when a smaller galaxy punches through a larger one, sending a gravitational ripple outward like a shock wave on water. Gas compresses along the expanding front as new stars ignite in a luminous ring, and the interior grows dim by comparison. Some rings are nearly perfect, others are warped, still carrying the memory of the impact in their geometry. Yet even here, gravity turns catastrophe into a new kind of order. Between these categories, the universe hides stranger extremes, diffuse ghosts and compact relics, giants assembled by countless mergers, loners drifting between structures. In the end, all of it folds back into the same theme. Galaxies are not fixed sculptures. They are processes. They jostle, merge, shed, ignite, and fade slowly, patiently, until even the most chaotic past becomes a smooth present. And far in the future, as expansion continues, there is a haunting possibility. Most galaxies beyond our gravitational neighborhood will slip beyond what can ever be observed, their light stretched thinner until it no longer arrives. The sky would look smaller then, quiet, local, deceptively simple. But we live at a time when the wider story is still visible, when collisions still leave tales we can trace, when faint ghosts can still be found, and the universe still has enough light left to tell us what it has been doing all along. If you're still awake, you can continue to the next chapter. Otherwise, I hope you sleep deeply and dream gently.